50 meters beneath the suburbs of Tokyo, there is a room so large that a 6-story building could stand inside it and still leave space above. That room was not built for people. It was built for water, hundreds of thousands of tons of it, arriving fast, arriving angry, and needing somewhere to go before the streets above drowned. The question is not whether a structure like this could exist. It does exist. The question is, what drove a city to dig this deep, spend this long, and build this large? And whether the engineering that resulted actually solved the problem it was designed to solve. To understand what was built here, you have to understand what Greater Tokyo looks like from above during typhoon season. The region sits at the convergence of several major river systems. When heavy rain hits, those rivers swell faster than their banks can contain. For decades, neighborhoods in the low-lying areas of Saitama Prefecture, just north of the city center, flooded repeatedly. Streets became canals, homes filled with water. Emergency services were overwhelmed. The flooding was not a rare catastrophe. It was a recurring condition that residents had simply learned to endure. City planners and civil engineers recognized the core problem by the late 20th century. The rivers were not failing. They were doing exactly what rivers do. The infrastructure surrounding them had simply never been designed to handle the volume of water that a modern, densely paved metropolitan area funnels into a natural system during a major storm. Pavement does not absorb rain. It redirects it. And in Tokyo's case, that redirection had nowhere productive to go. Work on the solution began in 1992. The project that engineers designed was by any measure an extraordinary commitment. The metropolitan area, outer underground discharge channel, known informally as G-cans, was conceived as a subterranean bypass for floodwater. Instead of allowing overwhelmed rivers to spill onto streets, the system would intercept the overflow, carry it underground, and discharge it into the Edo River, which had the capacity to handle the additional volume and direct it safely toward the sea. The engineering challenge was immediate and severe. The project needed to move enormous quantities of water with enough speed that the system could respond to a storm in real time, not hours later. And it needed to do this beneath a living, functioning city, under roads, under buildings, under other infrastructure, without disrupting the surface above. The designers answered with 5 massive concrete silos, each standing 65 meters tall and 32 meters across. These are not pipes. These are vertical shafts, each one essentially a hollow concrete cylinder dropped into the earth, positioned at intervals between the city of Showa and the city of Kasukabe in Saitama Prefecture. When a nearby river overflows, water enters the top of one of these silos and falls. The sheer drop dissipates the water's destructive energy. By the time it reaches the bottom, it is moving more slowly and is ready to be redirected. Connecting all 5 silos is a tunnel system running 6.4 kilometers in total length, bored 50 meters beneath the surface. Water that enters any one of the 5 inlet silos can travel through these tunnels toward the central discharge point. That tunnel is not a narrow pipe. It is wide enough to accommodate significant flow from multiple directions simultaneously, balancing the load across the system during storms that might affect one area more heavily than another. At the end of those tunnels sits the structure that gives this project its informal name, the Underground Cathedral. Engineers call it the water tank or the pressure regulating tank. Its measurements are almost difficult to process at first. 177 meters long, 78 meters wide, and 25.4 meters tall. 59 concrete pillars, each one massive in its own right, rise from the floor to the ceiling. The space they create feels less like infrastructure and more like something from another civilization's architecture. And yet every dimension serves a precise function. The pillars are not decorative. They support the ceiling of the tank against the weight of the earth above. Without them, the roof would collapse under the pressure of the soil and any structures sitting at ground level. They also create turbulence within the space, intentional turbulence that further reduces water velocity, preventing the pumps downstream from receiving flow that would damage them. Those pumps are the final active component in the system. 78 pumps, each rated at 10 megawatts, are tasked with moving the water that has collected in the pressure-regulating tank out into the Edo River. Together, they are capable of pumping up to 200 metric tons of water per second. That number is worth sitting with. 200 metric tons per second is roughly the volume of 4 Olympic swimming pools every minute, sustained continuously for as long as a storm demands it. The project reached completion by early 2006, after approximately 14 years of construction. Building underground in a densely populated urban environment over that span required managing not just engineering constraints, but also the practical reality of digging beneath active streets and neighborhoods without causing subsidence, service disruptions, or structural damage to buildings above. The scale of this system raises an obvious question about cost and consequence. A project of this complexity, duration, and physical scope does not come without trade-offs. The construction required years of resource commitment from municipal and national authorities. The pumps require significant electrical power to operate during storm events. Maintenance of a structure 50 meters underground, reached only by descending into shafts that most people will never see, is a permanent operational obligation, not a one-time investment. There is also the question of limits. The system was designed to address the flooding conditions that existed and were projected at the time of its conception. Climate patterns shift. Rainfall intensity in typhoon-prone regions has shown variability over time. No infrastructure system can be designed against every future scenario, and the GCAN system is not an exception to that reality. Its designers built to the problem they could measure. What lies beyond those parameters remains an open question. What is documented is the outcome as of the system's operational period. The Metropolitan Area Outer Underground Discharge Channel stands as the world's largest underground floodwater diversion facility. It intercepts overflow from the city's major waterways during rain and typhoon seasons and redirects that water to the Edo River. The 5 inlet silos, the 6.4 kilometers of connecting tunnels, the 59-pillar pressure tank, and the 78 discharge pumps function as a single integrated system, one built over 14 years and located entirely out of sight beneath a city of millions. The lesson here is not that engineering can defeat nature. It is that engineering can change the relationship between a city and the natural systems it was built alongside. Tokyo did not stop its rivers from flooding. It built a parallel path for that floodwater, a path that exists only underground, invisible to the people who benefit from it daily, operating automatically when the rain gets heavy enough and the rivers begin to rise. The structure beneath Saitama is not a monument, it is a machine. The cathedral-like quality of the pressure tank is a byproduct of function, not an aesthetic intention. And that distinction matters because it reframes what the engineers actually accomplished. They did not build something beautiful. They built something that works. And the scale required to make it work is what created the beauty as a side effect. 50 meters down, in a room supported by 59 pillars, the water moves. Whether the next major typhoon will test the system's upper limits, or whether changing rainfall patterns will eventually demand something even larger, no one can yet say with certainty. What the engineering record does confirm is that when the problem was clearly defined and the commitment was sustained over 14 years, a solution was possible, and it looked nothing like anyone above ground would ever have imagined. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.